No GPU, no engine, no graphics library. Lesson 1 put a pixel on the screen in C. Lesson 2 showed that a program is only bytes in a file. Today those two facts meet. The screen is bytes as well, and from here on we write them ourselves. No library, no graphics call, and nothing between this program and the glass. By the end of this there will be 7 pictures, and every one of them is the same single idea with different numbers in it. Volkov Commander as an editor. A new file pixel.asm. The same 2 lines as last time, a COM file, and it starts at 100 hex. Then a jump over a gap we are going to fill later. There is nothing between here and boot yet. By the end of the lesson there will be 3 routines in there, and this jump is how the program steps over them. Now the machine. CLD says the string instructions count upwards. We will need that in a minute, and it only ever has to be said once. Mode 13 hex, 320 by 200 in 256 colors, and we ask the video BIOS for it exactly the way lesson 1 did. And this is the line that matters. ES is going to be the screen, not point at it, not describe it be it. Segment 1000 is where the video card keeps the picture, and from now on ES colon anything is a pixel. Now the DAT. Row 100, column 160, the middle of the screen. And here is the only arithmetic in the whole lesson. The offset is y times 320 plus x. And that is the pixel. 1 byte, 15 is white, and writing it into memory is the entire operation. There is no draw call underneath this, because there's nothing underneath it. Last, the way out. Mode 3 puts the text screen back. This program owns the video card, and nobody is going to tidy up for us, and then we exit to DOS. Remember where those 4 lines are. They are the end of the file, and they are going to stay the end of the file all the way through. Everything we add today gets added just above them. F2, escape, and Control-O for the DOS screen underneath. 1 command, source in, program out, no linker. And nothing happened, or rather everything happened, far too quickly to see. The screen went to mode 13, we wrote our byte, and then the program finished and DOS took the screen straight back. Which is worth sitting with for a moment, because it is the first real difference between this and any language you have used. Nothing is waiting for you. There is no window that stays open, no event loop, nobody keeping the picture alive. The moment the program ends, the machine belongs to something else. So we have to stop and ask, and since we are going to want to stop 7 times today, it goes in once as a routine in that gap we left after the jump. Interrupt 16, function 0, sleep until somebody presses something. Same doorbell as lesson 1, different door. And while we are here, if that key was escape, leave altogether. 27 is escape. Now look carefully at these 2 lines, because they are the trap from last lesson wearing a different hat. The obvious thing to write is JE by, but by is the last 4 lines of the file, hundreds of bytes away, and conditional jump on an 8086 reaches 127. It cannot get there. So we jump over an unconditional jump, which has no such limit. And this matters more than it looks. The assembler would not have complained. It would have quietly used the 386 version. The program would run perfectly on every emulator, and it would die on the machine it was written for. Now use it, down to the bottom, and in just above those 4 lines. There it is, 1 white dot in the middle of a black screen, and it stays there because something is finally waiting. 1 byte, that is the whole of computer graphics on this machine, and everything for the rest of this series is that byte, written more times. Now a question, if 1 byte is 1 pixel, and a byte holds not to 255, what do all 256 colors actually look like? Let's just write them all down and find out. Start at the beginning of the screen, and add color 0. 64,000 bytes, that is 320 times 200, the whole screen. STOSB is the one instruction this lesson is built on. Put AL where ES:(DI points, and step DI on by 1. It is the machine doing what we have been doing by hand. Then add 1 to the color, and go round again. At 255 it rolls over to not on its own. A byte cannot do anything else. And there is every color this machine has. But look at the shape of it, because nothing in what we just wrote said where any color should go. We only ever said the next one, then the next one. So why is it slanted? Because a row is 320 bytes and there are only 256 colors. 320 does not divide by 256, it leaves 64, so every row begins 64 colors further along than the row above it. Every row is shifted, and shifted rows are a diagonal. Which is the thing I actually want you to take away today. The screen is not a grid. It is one long row of 64,000 bytes, and it only looks like a grid because the card reads 320 of them, drops a line, and reads 320 more. If it were really a grid, that picture could not lean. Now something that sounds trivial and is not. How do you clear the screen? You write not into all of it. Beginning of the screen, color not. And here we go 2 at a time. 32,000 words instead of 64,000 bytes, same memory, half the instructions, and the processor was always able to do that. REPSTOSW, one instruction, and it repeats itself until CX runs out. That is the entire screen clear, and it is one line. Black, which is not nothing, it is 64,000 bytes we deliberately set to naught. Because on this machine the screen holds whatever was last put in it and nobody clears anything for you. One word of warning while we are here, because these two instructions get confused constantly. STOS stores it, puts AL or AX where ES:DI points, and it needs no source. MOVS copies from DS:SI to ES:DI, and it needs something to copy from. There is no page of zeros lying about to copy, so filling is the right instruction. MOVS is Max lesson's whole subject. Now 2 lines, and the only reason we draw both is to see what they cost. Across first, row 100, starting at column 60 in white. 200 pixels across, and that is the whole line. One instruction: the pixels of a horizontal line are neighbors in memory, so the machine can just run along them. Now down, column 160, starting at row 40 in yellow. And this one cannot be a single instruction because the pixel below is not next door. It is 320 bytes further on, so it's a loop, and it's 120 times slower than the other one. Two lines that look exactly as important as each other, and one of them was free. That difference is not a curiosity, it is why every single thing in the games I write is drawn in horizontal strips. The terrain, the aircraft, the cockpit. It is not a style, it is what the memory layout charges you, and you can either pay it or arrange not to. Next, a square, and this time I am deliberately not going to clear the screen first. Red, and the top edge, which is a horizontal line, so we already know how to do it. The bottom edge, 80 rows further down, same instruction. And the two sides in one loop, because they are the same rows, one at column 40, the other 239 bytes along the same row. And there is the square with both lines still running straight through it. Nothing removed them, because nothing on this machine removes anything. There is no scene, no list of objects, nobody keeping track of what is on the screen. The screen is 64,000 bytes, and it holds whatever was last written. That is why the black frame a minute ago had to exist at all, and it is why a game that forgets to clear is a game playing on top of the wreckage of its last picture. You will meet that bug. Everybody meets that bug. A filled square, next, and there is nothing new in it whatsoever. It is the horizontal line from a minute ago, done once per row, which means it wants to be a routine, so up to the top. DI is the top left corner, AL the color, BX the width, DX the height. One row and there is our single instruction again, the same one that drew the whole line. Then back to where the row started and down 320 bytes to the next one. And to use it, 4 numbers and a call. "48 rows, and each of them was the line we already knew how to draw. Nothing was invented between the two pictures, which is roughly how all of this works. There's no moment where it gets complicated. There's only the same byte, written in last one, and it needs something that looks like chance. So, a number generator, 5 lines, back up at the top. Take the last number, multiply it by something awkward, add something else awkward, and keep the bottom half. That result is the next number, and also the seed for the one after it. Now 200 squares in random places in random colors. AND with 255 keeps the bottom byte, so X lands between 0 and 255, and since every square is 48 wide, it can never run off the edge. And the offset is once more, and for the last time today, Y times 320 plus X. Every picture in this lesson has been that line. "200 squares, and every one of them went through the same routine that drew the green one. Now watch this, because it is the most useful thing in the lesson and it takes 10 seconds. Run it again. Identical, square for square, color for color, in the same places. Nothing in that generator asked the machine what time it was started from the same number and did the same arithmetic. And that is not a fault to be fixed. It is the single most valuable property in this whole series. 2 bytes of seed instead of a stored picture. Change those 2 bytes and you get a different world. Keep them and you get the same one every time. It is how the city in these games is built. And it is how 2 machines on a network end up flying over identical ground without ever sending it to each other. 7 pictures, 237 bytes, and 1 piece of arithmetic underneath all of it. Offset equals Y times 320 plus X. No library was called, because there is no library. Nothing was cleared for us, nothing was kept alive for us, and nothing stood between the program and the glass because on this machine there is nothing to stand there. And if you want to do this rather than watch it, there is a DOS prompt in the description with this assembler already on the disk. Change the 15 in the first frame to a 4 and build it again. That is the whole point of it being a page and not a video. Next time, we make it move and it tears, horribly, because the card is reading the picture while we are still drawing it. That is where the second screen comes in and where MOVS finally gets its turn.